Hello, in this presentation I will describe a process separation model and analysis for domain-1 magnetic tunnel junction logic. Showing on the top left is the device diagram of a domain-1 magnetic tunnel junction, DW-MTJ. On the bottom of the device is a free ferromagnetic track with a domain wall that can be moved within the track by a spin transfer current flowing between the left input and the right clock terminals. On the middle, above the free ferromagnetic track is a tunnel barrier, and on top of it is a fixed ferromagnetic layer as a reference. Combining the free layer, tunnel barrier, and the fixed layer, this sandwich structure in the dash box forms a magnetic tunnel junction, or MTJ, that serves as the output of this DW-MTJ device. On the bottom is the image of a fabricated DW-MTJ. We can see the input electrode, output, and on the zooming and the insect on the right is showing the image of the MTJ. And DW-MTJ device is then used to implement Boolean logic gates. And in this case, we are showing the NAND gate and the buffers, and a buffer on the right. Those two are at the top of these two gates. So to efficiently design and simulate the device in circuits, we need a device model. This figure on the top left showing the flowcharts for two distinct modeling techniques for the DW-MTJ. The first combines micromagnetic simulation with SPICE to accurately capture both the magnetic and the electrical behavior of the DW-MTJ, but its computation load is heavy and therefore difficult to use for large-scale systems. The second technique is pure SPICE modeling, and here, based on the SPICE-only model, we integrate the parameter randomization into a model that gives us the ability to capture the impact of process variations to the DW-MTJ in the circuits. So basically, the expression showing on the bottom here is used to modulate one or more device parameters listed in the table on the right. With the process variation model, we can figure out which variation in the device fabrication are most severe and need more attention to ensure the correct functionality of the circuits and the systems. With the process variation model, we simulate a 1-bit full adder with DW-MTJs. As in the schematic showing here, this adder is constructed by a set of buffers and NAND gates we introduced before. On the bottom is the simulation results. The horizontal axis is the maximum variation range, and the vertical axis is the output error rate for the sum on the left and the carryout on the right. We can clearly see that the variation of different parameters have different impacts on error rate, and that the Cout has more immunity to parameter variations than sum. To be more specific, we divide the arrows into different input combinations. In these two plots shown here, we can find that some input combinations are more vulnerable to the process variation than the others, and the sum output in the adder is more vulnerable than the carryout. So, conclusions. First, the DW-MTJ is one of the few spintronic devices for which direct logic cascading has been experimentally demonstrated without any external buffering or amplification stages. That enables purely spintronic non-volatile computing system with no need for CMOS circuitry between devices. And to advance the development of this technology, we proposed a SPICE-only DW-MTJ model with random parameter fluctuations that supports investigation of robustness of DW-MTJ system to process variations. And the error rate of the DW-MTJ 1-bit full adder is evaluated with Monte Carlo simulation using this model, and this model also enables the identification of the most critical device parameter and input signal combinations, thereby providing understanding necessary for device and circuit optimizations for robustness and efficient operating of DW-MTJ computing systems.